why is this? This is the disk method, right? The washer method. Where does this formula come from? And to know that, we first have to know what we're integrating. So for the washer method, we have to consider a solid obtained by rotating a region bounded between two curves. What does this mean? So if we have a graph, right? Let's assume this is our x and this is our y-axis. And we have some line. We'll just call it a straight line for now. For example, y equals 2. We can obtain this by rotating the disk around some sort of thing. And you learned this earlier as to be a cylinder. When we rotate this around such an axis like the x-axis, we're left with a cylinder. We can do this again for a separate function. For example, let me get a different color. I don't have one, so we're going to call this line y equals 1. Again, we can rotate this around its axis again to get a second cylinder. Now we have two cylinders rotated around the x-axis of different lengths. From here to here, we know that this is 1 since y is equal to 1. And from here to here, we know this is 2 since y is equal to 2. Now we have this amount of data. We know that these are circles because they're rotated around a cylinder and it's symmetrical to each other. So we can express the area of any cross-section here as a circle. What is the area of a circle? Well, we know that the area of a circle is equal to pi times r squared. What is r? R is this. So we can replace r with 1 to get the area of a single cross-section. If we knew the length of this, which we don't for now since this cylinder goes off into infinity, we would also have the height and thus be able to calculate the volume of it. For the purpose, let's say x is bounded at 4. Sorry for the little messy drawing, but let's just say x is bounded by 4. Now we know the height of this cylinder is 4, right? So we have the radius of both the inner one and the outer one, as well as the height that they're both bounded by. So how do we find the area inside of this? Well, that's easy. We just take the big one and subtract it from the small one, because the small one is empty inside. If the big one is all of the space in it, and the small one is the space taken out of it, we can just do a simple subtraction problem. So in this case, pi r squared, pi r1 squared minus pi r2 squared is equal to the total volume of this outer one minus the inner one. So that leaves us with pi times 2 squared minus pi times 1 squared. Simplifying, we can take out the pi from both sides and simplify the squares, and we're left with 3 times pi. For this specific example, this works incredibly well. And it's very easy to see, as it's just like a simple geometry problem. But what if we were to make this a little bit harder? Let's say you're given some function on the f and y axis, right? We have no clue what this is. There's probably no reasonable way to express this graph, but for the purpose in mind, we'll call this function f of x. And now let's assume there's a second function inside of this function. We'll call this g of x. We've seen this before. This was our radius equation from our cylinders. So, for any function x, we can call this the same thing as y1. And this is the same thing as y2. Now we can just apply the formula that we applied last time, because we know when we rotate this, at any given cross-section, we will get a circle just because of how things are rotated. When you know, swing a towel in a circle or around, it forms a circle. So at any given point, we know that a circle will exist there. So by the definition of what we had to find earlier, by replacing r with our functions, we can get the exact same thing. So pi r squared, I guess it is, f of x squared minus pi g of x squared. And this is assuming that, this graph is assuming that f of x is bigger, or I guess bigger to g of x. This function must be bigger, otherwise you will be getting negative values, which is not real. We can take out the pi from this equation here, and we're left with f of x squared minus g of x squared. Now you're saying, where does the integral come from? Remember how I bounded that x equals 4? We can rewrite that by saying, rewriting it here. We can rewrite this by saying, this is the area between this and this. So for any arbitrary value a, any arbitrary value b, that is what your cylinder is bounded by. And that's where those things will take place. Putting the d of x at the end, this is where that equation comes from. You are finding the area of a rotated solid around this point, or around these two figures, cylinder 1 and cylinder 2. Hope this helps a little bit.